I see it as a step into the future, and it's exactly the thesis at Efficient. What we've developed is a next generation of architecture that avoids the limitations of specialization, of over specialization. That's the way that we think about it.
In this episode of Embedded Insiders, we're joined by Carnegie Mellon professor and founder of Efficient Computer, Brandon Lucia. Brandon dives into his company's general-purpose processor designed to deliver 100 times more energy efficiency than any chip on the market today. He also shares insights from his academic work and the challenges impacting the next generation of engineers navigating today's fast-evolving technological landscape. Later, Rich and Vin are back with another Dev Talk featuring Jonathan Pallant, senior engineer at Ferris Systems. Together, they discuss the growing popularity of Rust and why it could be a game changer for your next embedded design. But first, Rich and Ken kick off the episode with a rundown of what's in store and a sneak peek at upcoming podcasts.
Hello, engineers, developers, and friends. Welcome to another episode of Embedded Insiders. I'm Ken Briota, editor-in-chief of Embedded Computing Design. I am here with Rich Nass, our EVP and fearless leader, and with Tiara Oliver, our assistant managing editor. We're all very excited to get into this episode, so we won't keep you long.
Well, I want to talk about something Tiara was talking about, actually. We keep threatening to have on a guy who's runs an association whose charter is to connect the double E departments of the top tier engineering universities to industry. So the CEOs attend these events and the deans attend these events, and we're having scheduling difficulties, but very shortly we're going to have him on a Dev Talk with Rich and Vin. That topic is intriguing to me and so important, and we've been saying for years that engineers are not graduating with the skills that are necessary to start right away as engineers, and this group is trying to fix that. Anyway, I didn't mean to hijack the discussion.
Well, not at all. It is an interesting point. I mean, what the embedded engineering, electrical engineering, all of the pieces of this industry are changing so rapidly. You know, the freshmen who are coming into the engineering schools, the engineering departments now, who knows what they're going to be facing in 4 or 5 years when they graduate, in terms of just interacting with AI and interacting with, sensor fusion and all these other things that we're always writing about, not to mention the folks who've been out in the engineering field for 10 years who have to adjust the way they've been working on everything. So I think it's an important area of coverage. Aligning the engineering schools with where the industry thinks it's going and is going is a big deal.
And there's some self-interest there. The industry folks want to see if they can get the people trained before they leave universities, so they don't spend the time on the job actually training them.
Yeah, of course. It's interesting. The engineering world seems to be sort of accidentally turning into what law school has been, which is a training program to pass the LSATs, and then you get into a law firm and you spend the first 2 or 3 years there learning how to be a lawyer.
Yep, for sure.
I mean, what's new over there?
It isn't new because Rust is not new. The interest is new, and there is a lot of interest in Rust because it does a lot of things that some of these other development environments can't do, other languages. When we, for instance, security, if you're looking at doing something that has to be secure, you want to think about Rust. It has a lot of the things you need that are built in where you don't have to apply them later. So it does make sense.
Yeah. Well, folks out there, you're in for a treat. A couple of really nice interviews coming your way. So stick around and feel free to send us messages on LinkedIn. Tell us what you thought of the episode. As always, if you're not subscribed, make sure you subscribe, do the sharing, do the liking, do the following, and we'll catch y'all real soon.
Now, here's Carnegie Mellon professor and founder of Efficient Computer, Brandon Lucia.
The story goes something like this. We were doing research into resource-constrained embedded systems, computing applications like tiny satellites, energy harvesting infrastructure, monitoring devices, and wearables, things like that. And we were trying to add more computational capability. What you might today, you might hear people describe this as adding more AI capability. This was before AI was the renewed buzzword that it is today. Anyway, we're trying to push these features into those kinds of devices, and the more we pushed, the more difficulty we had, and we started analyzing, what's the limiting factor? We looked at energy. Energy was constrained. We looked at power. Power was constrained. What was really the problem, though, was the efficiency with which we were doing the computation was very low, and that was because we were using hardware that had been commercially available. This was almost 10 years ago, like I said. So we were using commercially available hardware that had been around for a very long time, sort of low power CPUs designed for these deeply embedded systems. And we had a sort of big idea moment at that point in the research. And we said to ourselves, well, we have an opportunity. We can do a clean slate redesign, start from scratch, do the entire computer architecture over again. And our goal with that, it was a high-minded ideological goal at the beginning, but it became increasingly practical over that period of almost a decade. A goal was to, at every point when we were in the design faced with the decision, make the decision that increased the energy efficiency of the system. So that's what we did. And we followed that thread where it led us, and we found some really compelling results, like some at times surprising results with respect to energy as we started to re-architect this system from the ground up. We developed the architecture that we are now it's going through advanced development and commercialization at Efficient, and the big benefits are it looks just like a conventional architecture from the programmer's perspective. You can use all your high-level languages, but when you run code on it, because the architecture is so fundamentally different from the classic, what we would call the von Neumann way of processing, the Efficient architecture uses 10 to 100 times less energy to do the same computation as you would do on say a CPU or an embedded low power CPU. So it's really a world of difference when you look at it from that perspective. And that's the reason Efficient exists. We're taking that technology, we're commercializing it, and we're making applications possible with that technology that just were not possible before this chip that we made.
Wow. I mean, I guess the big question here is like, how are you able to scale it down and get it so energy efficient? And why is it so different from traditional chips?
Yeah, I mean, that's the heart of what we're doing at Efficient. Efficient is in the answer to that question. I guess part of it is computer architecture. Before we started doing what we're doing, computer architecture had been living in the world of what's called von Neumann computing, and that's what most people think of when they think about how a CPU works. You sort of think of a big list of program instructions that is your software, and then one by one the CPU goes and sort of chunks through the instructions one at a time, and that means you have to go and pull the instruction in and decode it, and then there's a bunch of fidgety little bits inside of the processor they're like configuration bits, and they correspond to each different instruction in the program. Then you have to go and get the data that you're going to process, and moving data around inside of a chip that has a cost too. So you have to move the instructions around. You got all these configuration bits you're twiddling around, and then you have to move data to keep the operations fed with their inputs when the program is running. That's how things used to work, and that's very expensive. All of those factors I just listed are very expensive, especially when you look at energy. So we did an analysis of this. This was a million years ago now, and we're not the only ones that have done this analysis. Others have done this analysis too. Where does energy go when you run software on a von Neumann processor? If I say to my processor, by way of writing a C program, that I want to add two numbers together. Most of the energy, like high 90s% of the energy that gets spent, doesn't go into adding two numbers together. It goes into all that other stuff, moving instructions around, twiddling configuration bits, internal circuitry inside the chip, and then moving data around. And so we saw that and we thought, like, this is the problem. Instruction supply, internal configuration, and data movement. And we designed a new architecture that just fundamentally eliminates those as energy consumption factors. And the type of architecture that we developed is called an energy minimal data flow architecture, spatial data flow architecture. That's different in a number of ways. The sort of gist of how it works is, imagine a grid of processing elements, and they're like less than a core, each one of them. They're not quite all the machinery of a conventional CPU processing core. And we compile the program using our proprietary compiler technology, and we're able to extract the operations from a program and how the operations interact. And that all happens in the compiler beforehand. And then we can take those operations and the interactions between them, and we can map them onto that grid of processing elements. And that's what makes up our architecture. So now the program just starts running. Those operations are mapped onto the grid, and the program just kicks off and starts running. There's no instruction fetching. There's no internal configuration bits getting twiddled. And the data movement that happens goes directly from one operation to another operation through a highly energy optimized on-chip network that we've implemented also as part of the implementation of our architecture. And that's all in hardware. So we avoid those really fundamental costs that make von Neumann processing inefficient with respect to energy. And we're able to capitalize on that to the tune of, like I said, 10 to 100 times improvements in energy. We went to great pains here to make sure that this is all general purpose. Strong belief, strong motivation, and part of our vision at Efficient is that general purpose computing is extremely important for real world applications. And so we're focused on not just providing energy efficiency, but also the generality of high level programming languages and the way that people think about software today.
I'm glad you just brought up the general purpose computing and the fact that that's what you guys are aiming towards, because obviously AI is the thing today. And I know that you said that AI specialized chips are actually slowing down computing innovation. And I kind of just wanted to pick your brain some more and ask why is that, or why you think that.
Well, I wouldn't say that they're slowing down computing innovation.
Okay.
So AI chips, they have their place. Their place is where the workload is nothing but a single type of computation fixed in silicon and metal today and never to change from now through to the future. That is, except in a very small few use cases, an unrealistic interpretation of real applications. Most real applications that we encounter in customer use cases are highly dynamic. They're changing all the time, incrementally from sort of minor generation to the next, and also not so incrementally when there's major updates. Think of going from a pre-deep learning version of an application that uses conventional signal processing to something that uses, heavy use of deep learning. So the ability to adapt and to handle anything that comes along is very important from a general purpose perspective. The second thing is related to it's also related to the pace of innovation. General purpose allows programmers to be experimentalists and to try different kinds of things as part of their application. And this really is about, to the point in your question, this really is about innovation. If you have a fixed purpose substrate, it's an exercise in constraint that forces creativity in some sense, but it also ties the hands of the application developer. They have to fit their application into whatever the hardware does well. If it doesn't fit, too bad, you have to make it fit. if you have a general purpose substrate on which to run computation, you can be more of an experimentalist and you can use the solution that fits the problem rather than the solution that fits the hardware. That's a good way to do things. So those are two of the reasons that generality is really important. Generality is also important. This is like a little less intuitive, but it's also very important from the perspective of energy efficiency. So if I have an application that does AI encompasses a lot of things. It's not just machine learning. There's usually a data acquisition, like sensing phase. There's a data cleanup and signal processing phase. There's usually some machine learning stuff that happens in the middle. And then there's some back-end analytics. And so if I make an accelerator that's really, really good at doing the machine learning part, and a lot of the AI accelerators in the market today, that's what they're good at. And they do an amazing job. They can drive down the energy and drive up the speed of those things really well. Let's say it takes that machine learning part and makes it just infinitely better. So it's essentially, we don't have to worry about that anymore. Well, what you're left with is all the rest of it. So the signal processing and the data cleanup after you acquire the sensor signals and all that analytics. When we talk to customers, they tell us that in some of their applications, that's 50% or more of their application is in that other stuff that isn't the machine learning. We've actually had customers tell us, well, hey, we can't really use machine learning accelerator chips because our applications are too diverse. They wouldn't work for us. And so generality is not just good for supporting the whole application and language support, but it's actually like it's kind of key to efficiency, because if you don't optimize the entire application, then you're just going to get killed from the energy perspective by the parts that you can't optimize.
Yeah, that's really interesting. I feel like for those who aren't in this industry, you would assume that AI chips would be the answer to everything, or that they would at least be, beating the expectations of the general purpose chips. So, looking at that, do you see a shift away from like maybe hyper specialized AI chips near the future, and maybe us going back a little bit and focusing more on general purpose and energy efficient processors?
I see it as a step into the future, and it's exactly the thesis at Efficient. What we've developed is a next generation of architecture that avoids the limitations of specialization, of over specialization. That's the way that we think about it. And we enable the use of general purpose applications on our hardware with the efficiency that is in some cases better than accelerators we find in the market, or at least parity with accelerators that we find in the market. What we've shown with our architecture is that it's possible to have generality and also to have extremely high energy efficiency. The turn to specialization was essentially more of a concession than needed to be made when the goal was declared to be energy efficiency. That's one way of doing it, but it's essentially over designing for efficiency and giving up on something that's arguably even more important, which is the generality of the thing. So you can get extremely high efficiency for only a small subset of the application, or a 50-50 subset of the application, but you're stuck on the rest of it. And so you end up, it's actually really a tough spot for the application developers in these cases. What they end up with is part of the application works extremely well. It turns into a total, hot rod. It's super fast. It's super efficient. They don't really need to worry about it anymore. They can write their PyTorch code or their TF Lite for embedded systems or whatever, and everything works great. But then the rest of it, we've had people cook up demos that have like an i3 or an i5 sitting there next to their ML accelerator and burning 5, 10, 20 times as much energy. It sort of doesn't make any sense, but that's the corner that people are backed into. Another direction that people end up going, and this is one where we've heard plenty of stories about this, is some customers take their application and they try to make it work on the accelerator, and it doesn't fit the accelerator model. And so they think, well, we need some hardware improvements, so let's go FPGA. And they work on something like an embedded FPGA. And the issue there is that you don't get the efficiency of specialized hardware. So it's not really the same thing. You don't get the efficiency of what we're doing at Efficient on most FPGAs. And the programming models is really cumbersome. You have to write things in RTL code, like System Verilog, and that's not, if you talk to the average application developer, that's not their native language. So you need like a specialist team, and it's a big bootstrap to get an application working on the FPGA. So it's like you're backed into one of several not very nice corners. You're faced with an unsatisfying dilemma as an application developer. If you only have an accelerator that supports part of the application. So you get the generality, and it kind of digs you out. And this is front and center for us at Efficient. This is of great strategic importance for us. We're able to provide generality without making a compromise on efficiency. So we can get that, orders of magnitude improvement in energy, and you can write all your code the same way you've written it for embedded CPUs for forever.
Being in the position that you are and, teaching your students, and these engineering students are currently, in an age where there's so many different options to develop. And of course, we're talking about AI and how that's everywhere. Kind of what is your approach to, getting them started or getting them innovating in this world where there's just so much going on?
Yeah, this is a good question, and it's actually tough because things move so quickly. So, like I said before, Efficient spun out of work that we had been doing at CMU for 10 years. 10 years ago, when I started at CMU, most of the world was not yet talking about AI. No one was talking about energy except for a few people in a niche in academia. There's a few papers I like to point to from the academic literature that say, hey, energy is important, pay attention to this. And then an overwhelming amount of the academic literature, and then the industry trends that follow that, were not focused on energy one bit. And so we started into this world understanding the importance of this, in advance of that shift, where now it's like AI and energy are the only thing anyone's talking about. That's the most important thing. So things can change over a 10-year period. Things can change really just quite dramatically. So I guess my point here is it's tough to anticipate what is going to be important if you look at the moment in time where we are right now. So if I'm giving advice to future engineering students, it's tough to say do this, do that, and look at some particular thing, some trend or some new language or something like that, and say like that's the safe bet to make. That's the one to use. It's hard to say, is that going to have longevity for 6 months or 6 years or for the rest of all of computing? Who knows? One thing that I do think is really important is engineering students developing strong intuitions about the fundamentals in their area, whether that's thinking about circuits, if you're getting into embedded systems and you want to understand the fundamentals, or thinking about digital design, if you're getting into computer architecture, or thinking about even fundamentals of algorithms and systems programming, if you're getting into the software world. You can vibe code your way out of most problems. I think most people could, go into average software development job, and through a combination of ChatGPT, Stack Overflow, intuition, asking friends, Copilot, whatever, you can end up with something that pretty much works. But if you don't understand how to solve a novel problem when you encounter one, you might be getting a suboptimal solution. You might be getting a solution that has limitations you don't understand. You might be getting a wrong solution that you're unaware of. So I would say that an important thing to keep in mind is these tools are amazing. Embrace the tools, follow the trends, and see where things are going. But always have a strong foundation of fundamentals so that you can use problem-solving skills and a reasonable assessment of the fundamentals to make good judgments. Because those things they'll only be just as good as they are, and no better. It's important to really understand your field for these things to work. Things have changed significantly. When I think of our engineering team at Efficient, the students that we're looking at hiring today, their resumes look substantially different than resumes that I would have been considering 10 years ago. We have an incredibly strong engineering team at Efficient. I think our team just honestly couldn't possibly be stronger. It's an amazing group. We've brought together. And the reason for that is we have people that, like I was saying a second ago, they're deep experts in our area, and they have a willingness to take risks and learn and to understand the fundamentals. So like as far as, classroom strategy, I'm not going to say this is better than that. But I think that something I will say is that a focus on understanding, why are things the way they are, and being able to ask and ideally eventually answer hard questions about why things are the way they are. That's really important. That's where the fundamentals come in. I think that it's an anti-pattern for education is learning just enough that you can, do hello world in your favorite language and then Stack Overflow your way to a solution. That goes as far as it goes, but it doesn't lead to the deep insights that are required to, create something like we've created at Efficient, where we needed to rethink things from the ground floor. We erased the whiteboard and started over. And we could only do that because the team that we'd assembled, they understood this field inside and out. And we were able to really push the envelope in terms of what we're doing. So I would say in terms of education, it's important to, embrace what comes along. Like I said before, these new AI-based coding assistants, that's what always comes to mind for me is, I actually am a user of these kinds of question answering and interactive assistant type tools. I think they're great. They're very useful for what they are. But I'm not gonna stop learning by doing just because we have access to these. I think that would be a mistake. And so I think, framing this in terms of advice for up and coming students in this area, like make sure you understand why you're doing what you're doing, and then don't lean on those tools too much. What we're doing at Efficient is really something unique, and it's a break from basically 75 years of doing computing the same way. What we're doing is unique because it allows application developers to do general purpose applications for 1 to 2 orders of magnitude less energy than any other general purpose compute hardware in the market. So we're offering something really unique. And this June, when we field our first product, when we launch our first product to our lead customers, we're really excited to see how that materializes for real world applications and moves the needle and makes things possible that are just not possible using existing technology.
Now, here's Rich, Vin, and Jonathan Pallant, Senior Engineer at Ferris Systems.
And here we are with yet another episode of Dev Talk with Rich and Vin. I'm Rich Nass with Embedded Computing Design. The other guy at the other end, who is quite formally dressed today, is Vin D'Agostino,
Hey, Rich,
Embedded
how are
Systems
you?
Developer. How's it going, Vin?
Great. How are you?
I've actually been better, but I won't bore you with my problems. But why the formal outfit?
I'm actually on campus at Stevens Institute, which is my alma mater right down the road from yours, and working with some students. And you won't believe, but I'm actually meeting a tailor today, and I thought I would dress up for the tailor.
So you dressed up for the tailor, but not for the students.
Well, I've dressed up for the students. Actually, the senior design professor, his class is meeting today, and I know him, and he said, "Oh, you're on campus. I want you to talk to my class." So I have to go in and talk. So I figured I would throw the jacket and tie on, and I'd see my tailor, and I would be a little more formal when I'm standing up in front of 40 students, telling them what the world is going to be like when they get out.
Is
All
the
of that,
tailor
so-
going to talk to the students too?
The tailor will not talk to the students, and I suspect, although they get paid a lot more than you and I did when we graduated, that it'll be a while before they can afford custom tailored suits. So.
That's for sure. That's for sure. So the fact that you're there and you're speaking to students, and I know you're doing a little bit of teaching, that's a good segue into what I want to talk to you about.
Okay.
Rust. Are you familiar with Rust?
I assume you mean the programming language and not the stuff that appears on top of steel when it's left
Well, it's
unprotected.
actually, okay, let's go back to my problem. I got it in my shoulder, and I've been going to physical therapy because I got this rust in my shoulder. But anyway, let's not go there. Yes, I'm referring to the language Rust.
I'm familiar with it, but I have not done any major projects with it. I wouldn't call myself conversant. I know some stats about it because I talk about different programming languages when I'm teaching embedded systems because, they are much more resource constrained than if you're designing for the desktop or a server or cloud application. And so we talk about what it means. Everyone wants to program their micro in Python. I'm like, oh, okay, well, that's 78 times the amount of energy and it's, 30 times the size and it's, however much more execution time. So let's talk about what it means to pick a language or pick a peripheral or even pick a data structure and have that affect the size and running speed of your code. I think I've said this before on the podcast, but the first day of class, I say, look, the difference between a software engineer and a firmware engineer is that software engineers assume they have infinite resources, and we are way smarter than that. So, and that's how we start. So that's essentially everything I know about Rust.
Well, I sort of bring it up because it was introduced to me a few years ago, and it sort of got a lot of hype, and then it went away, and then it got some more hype, and then it went away, and then at Embedded World not too long ago, there was a fairly sizable amount of interest in it. I saw a bunch of people, so I said, okay, I should probably learn more about this because I think this is here to stay. So with that, I said, okay, let's find myself a Rust expert who we could bring onto the podcast. And I found Jonathan Palant. Did I say that right, Jonathan?
It'll do for me.
Okay, it'll do for you. And he's a senior engineer at Ferris Systems. So how are you today, Jonathan?
I'm doing great. Great to be here.
Good. So do you qualify as my Rust expert?
I'm happy to give it a go. No one's been doing Rust for 2 decades because it's not been around that long, but I've been at it for about 8 years now. So yeah, let's see if I can answer your questions.
Okay, so the first question, why are we seeing this resurgence? I mean, it hasn't been around that long, but I was going around Embedded World, as I said, a month ago, and people wanted to talk about it. Why? What's going on? Something new?
I think there's a couple of things that are going on. So from my point of view, Rust never went away. There's been a bunch of us engineers both writing firmware in Rust and taking part in the Rust project itself, kind of working on the tool chain and things. I think recently announcements we've heard from the US government have kind of helped. So the former administration was saying, you need to take software reliability and security seriously. It's a big issue when people keep hacking these embedded systems. If you want to make everything an embedded system, you want to put wireless connectivity and all the things, you're going to have to start doing it properly. And we're going to start effectively judging you if you use a language that's not considered memory safe. And by that, we mean, is the language intrinsically going to help you avoid memory issues like buffer overflows? Is it going to help you with thread safety and avoiding data races and those kind of classic issues? And Rust has this kind of unique position of being a memory safe language, but it's also a systems programming language. So it compiles into machine code, and it can be the very first code your toaster, your microwave executes on startup. And that's not the case with Java or Python or C#, which are also memory safe, but they need kind of this runtime underneath them. So I think, people starting to take security on embedded devices seriously is one reason for the uptick in Rust. And the other is, I think there's been some major moves forwards in the qualification of Rust tools. So before there was just the open source Rust compiler, but now we've got a selection of commercial alternatives that come with qualification for use in safety critical use cases. And that's made people start to think, oh, actually, maybe if Rust can do that, maybe Rust can work for me as well.
So go back to that runtime underneath them. What exactly do you mean by that? And what is that runtime that you're running underneath them?
So if you want to execute code written in MicroPython on a microcontroller, that Python code doesn't execute in your processor. Your processor only understands ARM machine code or MIPS machine code or whatever it happens to be. And that Python code is kind of translated at runtime. And that is the Python virtual machine that's executing that code, and that's providing a bunch of services, the garbage collection, heap allocation, and all those kinds of things. Whereas when you write C code, you put the C code into your C compiler and it produces machine code that comes out, and there's nothing else required. It's like it's all there within the machine code, and that's enough to run the system. And that's where Rust plays. You can compile Rust code, you get machine code out. There's no runtime, there's no garbage collector, nothing else is required. That machine code is enough to get the machine running.
Interesting. Okay. Okay, I'll keep going. I thought you had a question there, Vin.
Oh, sorry, my audio kicked out for a minute. I actually do have a question. So one could argue that if you have a consistent support runtime environment for a language and it is secure and safe and certified, that any, let's say, scripting code you might write that runs on it, there's a group of people that I know in California who are trying to get everyone to write embedded systems in JavaScript. And they actually have a compiler, so it's not running an interpreted version of JavaScript. You write your script, you compile it down, it brings in the libraries that it says it has already checked and verified and everything. So let's assume that all those ducks are in a row. What makes a language like C or Rust different than those languages once they are compiled and running?
I think the major difference comes down to resource usage. I think if you look at history, people have gone to languages like C because they were able to get the job done using fewer kilobytes of memory and fewer clock cycles, which ultimately comes down to, fewer joules out of your battery. And if you can save, you need less RAM, you need a smaller battery, you can buy a cheaper processor from your silicon vendor's seemingly infinite catalog of parts. You save dollars on the BOM, and that's many dollars on the ticket price. And that just makes sense. So in these embedded systems, they're so often resource constrained and cost constrained. And sometimes you're not, right? Sometimes you're building 3 of them and they're going on a bench. And in which case, sure, go ahead, use MicroPython, use JavaScript. If that's what gets the job done within the envelope that you've got available, then that's a great choice. But very often, I've been an embedded systems developer for 20 years, built Bluetooth headsets and satellite modems, and we always had a very fixed set of constraints, and we needed to get an awful lot of compute done within that. And in the past, I'd have gone for C, and now I can go for Rust instead and be a lot more productive.
Well, you're right. People, something that people don't think about a lot is the implications of the things you learn when you take, let's say, a data structures and algorithms class, and you understand that the way you pick your data structure affects the kind of algorithm you could write, and the speed and size and reliability and even manageability long-term of the code that you've written. And if you pick the right data structure, your code can become much simpler. And that sort of leads me to, are these languages inherently slower and larger in size because of these runtimes that could be compiled and running just as quickly? Or is it the construct of the language where you're trying to make it easier for a programmer? So, some of these languages, you don't even have to type your variables. Like every variable is exactly the same. And so you don't have to worry about, is it an unsigned character? Is it an unsigned 16-bit? Is it 32 bits? Is it a float? Is it a single or double precision with the float? Whereas a language like C, where you're typing everything, you are able to control how many resources are used for this one temporary variable that's going to exist for a very short period of time, right? That's a significant difference between some languages when you look at the difference between C, C++, C#, Python, even looking at older languages like Pascal, COBOL, all of those, right? So,
yeah, for me, it's about layers of abstraction. The more kind of layers of abstraction we've got to work with, the bigger the giants whose shoulders we're standing on, the less work we have to do as developers, but the bigger price we're paying. And in any kind of firmware project, I would say actually that's a piece of systems engineering, because the firmware doesn't stand alone. It's got to run on hardware and be a product that's got to retail in the market. And yeah, you've got to pick like an appropriate level of abstraction. And I think that's where Rust is really interesting, because previously it was, you can have the nice things, JavaScript, Python, C#, what have you, but it's going to cost you in performance, or you can have all of the performance and you're going to be sweating in the, the coal mines of debugging hell for weeks on end, because a weird thing happened and everything crashed and you've got no real idea why. Where Rust has been able to move the needle is say, we'll give you all the performance of a C program. And all the evidence says Rust programs are about the same speed as a C program. I've seen some run 10% faster even, but we say broadly the same. So you have all the performance, but you can have all the productivity at the same time. You can have a standard library with nice data structures. You can have a compiler that's on your side that actually goes, hey, you've made a mistake. Line 5 doesn't work with line 7. I'm going to literally underline them in red and point a big arrow and say, yeah, you need to rethink about line 5. It doesn't work for these reasons. Here's a link. You can go and, read more stuff online, as opposed to, the C programming language comes from a time when you were lucky if the compiler said syntax error. It's a language designed for doing compile jobs overnight on punch cards. So Rust was able to give you the performance, but give you the kind of the productivity and the safety at the same time.
I would agree, but I would challenge you that's not necessarily a construct of the language, but a construct of the tools and the philosophy of building the tools for working with the language. There's nothing inherent in the language itself, because the language is just, as you said, compiling down to, opcodes or machine language instructions. And at that point, you could write safe and structured assembly language, but the language doesn't lend itself to that. I talk to my students all the time because, and people always say, well, I'm not going to use C, for example, and this is maybe a discussion 10 years ago, because I can write it smaller and faster in assembly. And I say, you know what? There was a time when that was true, but it's not anymore, because the tools have gotten so good that the compiler and the optimizer will find parallelism in your code that even if you saw it, you wouldn't write your assembly that way, because it would be unmaintainable. But at a high level, you can write it the way it's maintainable and it makes sense. And you can go back 3 years from now and say, oh, that's what I was trying to achieve here. And yet the tools can make it more efficient by finding this parallelism, reuse of code, a jump instead of a return, because it knows it's doing something else because it's looking ahead. So I think you can't look at a language anymore by itself. You have to look at the environment for developing it as well.
I think that's fair. I can give one example of where the tooling and the language kind of co-evolved. So again, looking at Rust, we have the idea of pointers in Rust, but we prefer the idea of references. And references are tagged with the notion of what are you pointing at and how long does that live for? And that kind of applies in C, but the human has to hold that kind of knowledge in their head. In the Rust language, there's actually a mechanism built into the language to say, I've got a function, it's going to take a reference, it's going to return a reference, but actually these two are associated. That thing I'm giving you back is actually just completely associated with the first argument you gave me, and you need to tie those two lifetimes together. Or maybe it's the second argument, or maybe actually the returned reference comes from somewhere else in the program. But when you don't have a language syntax to be able to express that then massively limits what the tools are able to do. People write static analysis tools in C, and they have to do a lot of hard work to kind of understand the program. Whereas when the language has been designed to allow for that kind of analysis, then it can be done a lot more easy, and it just sort of becomes a natural part of the ecosystem.
Yeah, a good example of that is null pointers, right? You pass a null pointer, that's a classic job interview question. So anybody out there listening who's about to go on a job interview, most people will say, write me an algorithm that takes, or write me a function that takes this and this, and the argument is a pointer. And if they don't test for a null pointer at the beginning of the function to make sure that the pointer is valid, then they immediately lose some credibility in the interview, right? Because there's always a possibility that a null pointer, gets sent for some reason. So I totally understand that. But now the question or the discussion is, are we better off making safer languages or putting that effort into training engineers better?
I think we can point to kind of history and say, if it was possible to educate engineers that they could just write perfect software, I feel like we'd have done it, because some of the mistakes they made are expensive. And I think there's also, I like to think engineers have a certain computational budget, right? There's a certain amount of brain power you can give to your job. And history has shown that if you can take some of that work away and teach the machine to do it, the humans use that spare brain power to build better and more interesting things, get their work done faster. And I think we can see with Rust that when we've taught the compiler to manage which items borrow from which other items and how long everything's living, and does this system even make sense, or is it kind of nonsensical because you've ended up with dangling references? By not having to think about that as a human, I'm free to spend my brain power on kind of more interesting problems.
Very good.
Okay.
So what are some of the application spaces that we should expect to see the more heavy use of Rust, and why?
It's really interesting because it's something about firmware developers. They don't seem to love writing blogs about how they do their day job, right? All the hyperscaler companies got into this 5 or so years ago. The Amazons, the Microsofts, and the Googles of the world, their back end is kind of in Rust now, and they wrote about it, which is great. I know a number of people are doing Rust in firmware on embedded microcontrollers. They don't love to talk about it. Sometimes I feel like they've discovered some kind of secret hack to making better firmware faster. But I can point to a couple of examples. Microsoft have a security processor called Pluton. It's one of the security thing. Firmware is written in Rust. So if you've got a Pluton chip, I'm pretty sure the shipping ones are running firmware written in Rust. Google have the same thing. They have a security processor in Chromebooks. It's written in Rust. If you go out today and buy certain models of Volvo and Polestar, I want to say it's the Volvo EX90 and the Polestar 2, other brands of vehicle are available. The cars shipping off the production line today, the low power management system is written in Rust. They had that done years ago, and that's shipping today. And I think you're going to see a lot more interest in the automotive space. I can't talk about who my customers are, but trust me, there's an awful lot of interest in that space, especially now qualified tool chains are available. I know a company is doing a 3D ultrasonic sensor. It's like a module you can fit to a robot to kind of tell you where you are in 3D space using basically the audio version of LiDAR. They're doing all the firmware in Rust, and they're going for SIL 2 certification. So that's going to be a really early example of Rust firmware actually used in a safety critical system. So I think there's going to be a lot more. I know there's a lot of projects that have started and are on the way, but those are some of the ones that I know are kind of further down the line.
Well, you're highlighting actually what I would call an inertia-based barrier to entry on this, which is if Microsoft were to support Rust in Visual Studio, you would start seeing a lot of desktop apps being written in Rust because it's there. And certainly for Windows-based programs, Visual Studio is probably the #1 environment in which people write their programs, right? On the micro level, every MCU manufacturer has their own set of tools, right? There's MPLAB X for Microchip. There's eSquare Studio for Renesas. There's SPM32 IDE or Cube IDE for ST. And so, and then that doesn't include all the private people like Sager and IAR and stuff who are supporting the industry. So you would have to get every one of those companies to say, we're going to support not just LLVM on C and GCC for C, but we're going to support Rust as well. And for them, the lift is that every code example they write to support a peripheral that's on the chip, they now have to have, multiple versions of these examples in order to understand how to use the peripheral in each of these languages. So how would the Rust community start to make that happen?
Yeah, it's a really interesting one. I describe these as islands, right? You're either on kind of Nordic island or TI island or ST island, and it's quite hard to sail from one island to the other. We saw that was a problem during the chip shortage, right? You're stranded on one particular island, you run out of chips. It's kind of hard to switch over. So a lot of the community work that's gone into the Rust embedded ecosystem is all around building abstractions where we don't actually care so much which chip you've got. We've got a standard interface, we call it a trait, that describes, for example, an SPI controller. And if you want to take your little LCD screen, it's written against that abstract trait. And so it doesn't actually care whether that driver is running on a chip from ST or a chip from Nordic, as long as the traits have been implemented, we would say in the lingo, for that particular device you're using. Now, currently, not a lot of silicon vendors doing that. That is something I do keep talking to silicon vendors about, maybe see a little bit of movement. I want to give a shout out to Espressif, the people who make the little ESP32 Wi-Fi chips. They loved what was going on in the open source community on their chips in Rust. So they basically hired them all. So Espressif now has a Rust team, and there is first-class support from them for Rust on their microcontrollers. We've also heard noises from Infineon supporting Rust on some of their automotive parts. And we saw a press release a couple of months ago from ST saying they were interested in Rust on some of their automotive parts. The other thing I would say is I've built embedded systems in the past where, frankly, I won't say which silicon vendor, but I looked at the silicon vendor stack and I gently swept it all into the bin. And then I wrote something bespoke for the application we were doing, because we were super critical on, the resources we needed. And so actually, you don't need to use the silicon vendor stack. We've got the information. You can just build it yourself. And if you're going to do that, you could do it in Rust as easily as you could do it in C. Again, it's trade-offs. Maybe resource usage is less critical. You'd love the leg up the silicon manufacturer is going to give you. And I would love to see more silicon vendors offering first-class Rust support. But in the meantime, the open source community, I think, is backfilling that admirably.
Cool.
So one last question from me. What language is it supplanting?
I get all kinds of people in my trainings, right? I get the diehard C developers who are being told or want to switch over to Rust. But I get Python and JavaScript people in my trainings who are like, yeah, we want to learn Rust because we'd like to keep all of the nice things. We'd love to have a language, with built-in dictionaries and lists, but we need the performance. So actually, I think it's starting in the middle, and I think it's coming for everyone.
Very good.
Okay. I have one last question, because
Sure.
you did talk about performance, and especially on the embedded side, clock cycles and memory are really important. And and it's been a while since I've looked at these stats, but there are people who compare programming languages. And you had said, and I agree, and the data supports that from execution time and even from an energy usage time, Rust is pretty close to C. If you consider C, the base, so 1.0, Rust is 1.03 in energy usage and 1.04 in execution time, comparing it to Python, which is 75.88 in use of energy. And you wonder why all these AI searches take so much energy, and 71.9, so almost 72 times the amount of time to run the same algorithm. When you look at code size, however, if the smallest is Pascal, but nobody wants to write in Pascal anymore. C is about 1.2 times that. So again, not too far. But Rust is
I see you've done your
1.5.
homework here, Vin.
Yeah, but this happens to be a slide that I use in class when we're talking about how green is your language.
Okay.
Now, this data is a few years old. So and people will find this data. So I want to bring it to light, because someone's going to say, well, okay, you talked about the two good things, you didn't talk about the bad thing. What advances have been made over the last 2 or 3 years on code size, because at the publishing of this table, the code size for Rust was about 1.5 times the size of C. So, but compilers tools evolve all the time. So tell us where it is now. And
Yeah,
as you said, relatively young. So
yeah, so that's fair. Some of this comes from Rust's standard library. Actually, Rust has 3 standard libraries wearing a trench coat. The top one is the thing that cares what operating system you're on. It does file systems, threads, and networking. The middle one has the heap allocator, and the bottom one is what we call libcore, and that's just your basic Unicode string handling, your basic data types like result and option for declaring, errors and whether things have been found or not. Now, that has all been developed, I think it's fair to say, with a primary focus on desktop applications, and they were super keen on performance, and they were relatively relaxed on choices that affected the code size, because it's a big desktop machine. That wasn't the primary focus. That focus is changing, but the problem you've got is you kind of need to pick one. Right? You've either got to choose whether you want to optimize your standard library for performance, or if you want to optimize it for code size, because these are in tension. So
Sure.
2 things. One, the Rust project are looking at ways they can allow you to make those kind of choices when it comes to using the core library. In particular, our version of printf tends to produce quite large code. It's quite good performance, but it does chew up quite a bit of code space. That is fair. And the examples, the numbers you get will kind of depend on how much sort of string formatting and printf style stuff you're doing. The other thing is, my company, Ferris Systems, we've developed a logging mechanism. It's an open source project. It's called DFormat, stands for deferred formatting. And what we do is we take your log messages and the arguments you want formatted within them, and we don't put the log string on the microcontroller. We put it into the debug section, and we replace it with a very simple integer. And then when it comes to logging, your log message says, please send log message number 5. The first argument is 6, and the second argument is Y. And the laptop then receives that, and that's only like 5 or 6 bytes of information. The laptop looks at the debug section of your ELF file and goes, you're printing log message number 6. All the string formatting happens on your laptop, where you've got all the time in the world to do it. So there's kind of one way to bypass the problem. You go, string formatting is kind of expensive in Rust. Let's simply not do any string formatting and move the problem elsewhere. And I've seen simple programs drop from like 60K to 5K just by taking out, in particular, floating point formatting is quite expensive. So yeah, people are aware of the issue, and there are some nice solutions to it.
Right. And I should also say for our listeners that those numbers I was giving, and because that's how they did these tables, was assuming a bare metal design. But if you are adding an RTOS or anything else to that, the size of the code grows automatically from that. And the stuff that is in Rust is essentially thread safe from the beginning when you're writing it. And so if you're going to work with an OS in C, you have to adjust those numbers in your thinking process when you're trying to compare it with Rust. So for those who are listening, that's an important thing to know about.
Very good. Well, thank you very much, Jonathan. I know I learned a lot here.
Yeah, my pleasure. It's been great fun. Thank you for having me.
Yeah, thanks for joining us.
That was Jonathan Pallant. He's a senior engineer with Ferris Systems. So what do you think, Vin? Is this thing gonna take off or what?
It's an interesting place to work. I think they have the same uphill battle that RISC-V has, in that the installed base and the thinking process is going one way, or they're trying to change it. And it's very much an ecosystem-based move. I mean, that's how ARM got and C got their stranglehold on where they are. So they took a bunch of stuff that was everywhere. Everybody had their own architecture, their own whatever, or their own assembly language, and they centralized it into a language that could run anywhere, and centralized it in in an architecture that everybody could use. And that's why everybody's proprietary ones kind of went away. And now we're dealing with a shift on the hardware side to RISC-V, and on the language side, we're looking at something like Rust that is challenging C, which is obviously the, you know,
Uh-oh, I think we lost you, Vin. So I think we're going to cut it off right there. Thanks, everybody, for listening, and we will see you on the next episode of Dev Talk with Rich and Vin.
Thanks for listening to this edition of Embedded Insiders. For more daily news, videos, and podcasts, visit our website at embeddedcomputing.com.